rocky world called TRAPPIST-1c hangs 2.4 million miles from its star. That is closer than Mercury sits to our Sun. One face bakes past 100 degrees Celsius, permanently. The other face stays locked below -200, permanently. No wind or weather redistributes the heat, because barely any atmosphere survives to carry it. The James Webb Space Telescope measured this directly, in real infrared light, not in a model. This is not the familiar green ring astronomers draw around a star on a habitable zone diagram. It is a frozen, airless hemisphere, sitting next to a scorched one. A hard line of permanent shadow separates the two. That line is the physical answer to a question astronomy keeps quietly dodging. If a planet sits inside that green ring, the so-called Goldilocks zone, shouldn't that mean liquid water, maybe even life? The ring only tracks how warm a world would sit if nothing else about its star mattered. For the coolest, most common stars in the galaxy, everything else is exactly what kills the planet. Here is the trap hiding inside almost every habitable zone headline you have ever read. The zone is defined using one variable, distance from the star. That distance is tuned so a planet's surface could theoretically hold liquid water. Astronomers announce a planet inside that zone, and the story usually stops right there, temperature alone, as if it settled the whole question. But for red dwarfs, the small, dim stars behind most recent habitable zone announcements, two other variables decide the real outcome. Neither one appears anywhere on that diagram. Those two variables are radiation and rotation, and they are not minor footnotes to check later. They are the forced consequence of the exact same closeness that let the planet qualify as habitable at all. Start with why that closeness is unavoidable in the first place. A red dwarf is dim by definition. Some put out less than 1,000th of the sun's total light. For a planet to receive Earth-like warmth from a star that faint, it has to orbit absurdly close, often 20 times nearer than Earth orbits our own sun. That is not a wide, generous band the way our solar system's habitable zone is. It is a narrow shell only a few million kilometers across, wrapped tightly around a barely glowing star. Picture standing near a small, sputtering campfire instead of a roaring bonfire. To feel any warmth from that small fire, you must stand right at the edge of the flames. You are warm there, technically. In the narrow sense a thermometer would confirm. You are also close enough that embers reach your skin constantly, stinging in a way distance would prevent. And standing that close, you cannot casually turn around to warm your other side. The instant your back faces away from the flame, it starts losing heat fast. Every comfortable habitable zone planet around a red dwarf stands at exactly that distance from its own fire. Close enough to be warm, close enough to be scorched, close enough that turning away turns dangerous. That single arrangement is the forced condition of the whole system. It creates two separate independent ways for a planet to end up dead. The first killer is radiation, and it starts with something counterintuitive about red dwarfs. They look calm and steady in visible light, dim and orange, nothing like the sun's blaze. But in far ultraviolet and X-ray light, the wavelengths that actually damage an atmosphere, these small stars turn shockingly violent, especially while they are still young. Flares erupt from a red dwarf's surface with startling speed. Because a habitable zone planet sits so close in, it takes the full undiluted force of every eruption. Proxima Centauri, the nearest star to our own sun, put on exactly this display in early 2018. Within roughly 10 seconds, its brightness spiked by a factor of 1,000. Instruments monitoring the star in ultraviolet light caught the surge happening in near real time. The flare lasted only minutes but carried energy comparable to a far larger star's worst day. Proxima b, the roughly Earth-sized planet orbiting inside that star's habitable zone, sits at just 0.05 astronomical units from its star. That is a small fraction of the distance separating Mercury from our own sun. That planet took the full blast of the 2018 flare directly, with essentially no distance to soften it. A single flare like that one would probably not sterilize an entire planet outright. But red dwarfs like Proxima do not flare once and settle down for good. Follow-up monitoring recorded further major flares from the same star within the following years. They flare again and again, repeatedly, across billions of years, with no long quiet period expected, hammering the exact same hemisphere over and over, without pause. The planet's locked orientation never lets a different face take the next hit. That repetition is the detail turning one dramatic event into a long-term mechanism. it is worth being precise about how the damage actually happens. Each flare strips away a little more atmosphere through a process scientists call ion escape. Radiation from the flare energizes charged particles high in the upper atmosphere, past the point where gravity can hold them. Those particles simply drift away into space, permanently lost. Hydrogen and helium, the lightest gases in any young atmosphere, go first. They get stripped away early and fast under repeated flare bombardment. Heavier molecules like nitrogen and carbon dioxide follow more slowly, escaping only after longer exposure. A planet does not lose its atmosphere in one dramatic afternoon. It loses it in countless small increments, spread across hundreds of millions of years. Researchers modeling this exact process, using computer simulations of the upper atmosphere's response to repeated flares, found something stark. Atmospheric loss rates roughly 100 times higher than any terrestrial planet in our solar system. 100 times is not a rounding error buried in a footnote. It is the difference between an atmosphere lasting billions of years and one vanishing within a few 100 million years, a comparative blink of geological time. The calculation gets worse without a strong planetary magnetic field to help deflect incoming particles. Earth generates exactly this kind of shield through a churning liquid iron core deep underground. Most small rocky exoplanets around red dwarfs show no confirmed field of that strength. A slowly rotating, tidally locked interior struggles to generate one. So the very proximity that lets a red dwarf planet sit in the habitable zone is the identical proximity exposing it to radiation. That same radiation erodes the atmosphere down toward nothing. Warmth and destruction, on these worlds, arrive from the exact same distance, through the exact same star. Proximity, though, does not only weaponize starlight against a planet's air, it also rewrites the planet's own rotation, through gravity alone, no flare required. When a planet orbits close enough to its star, gravity pulls harder on the near side than the far side. That stretching force is what scientists call a tidal effect, and it acts slowly but permanently. Over enough time, that steady stretching drags the planet's own rotation into sync with its orbit, the same basic mechanism keeping our moon showing Earth only one face. For a habitable zone planet close around a red dwarf, that locking takes only a few 100 million years to finish. Once locked, the planet stops rotating relative to its star entirely. One hemisphere then faces the star forever, in constant daylight, without ever once seeing a sunset. The other hemisphere never sees a single photon of starlight at all, trapped in permanent night. Picture that same small campfire once more. Standing close enough for warmth means you cannot rotate freely. You have to keep facing the flame just to stay warm. One side cooks while the other freezes the instant it turns away. A tidally locked planet lives inside that exact arrangement forever, not for one cold night. TRAPPIST-1z and c, two of the innermost worlds in that 7-planet system, carry this signature in real measured data. Nature Astronomy published measurements in April 2026 recording day side to night side differences exceeding 400 degrees Celsius. That is two nearly separate physical worlds sharing one small rocky body, permanently divided, with no rotation left to blend them. It is worth pausing on how fast the optimism around this exact system collapsed, and how thoroughly. When TRAPPIST-1's 7 roughly Earth-sized planets were first announced back in 2017, headlines called it a landmark discovery, one of the most promising habitability finds ever made, covered by outlets worldwide within days. 3 of its 7 planets sat comfortably inside the calculated habitable zone, using the standard temperature-only formula. Commentators speculated openly, sometimes excitedly, about oceans, weather systems, and possible atmospheres thick enough to support them. That optimistic framing held steady for years, mostly because the instruments needed to check any of it directly simply did not exist yet. The James Webb Space Telescope changed that completely, planet by planet, starting in 2023. Direct thermal emission measurements began quietly replacing speculation with hard, checkable numbers. Green and colleagues measured TRAPPIST-1b's dayside temperature in 2023 using exactly this method. They found no evidence whatsoever of a substantial atmosphere, just bare rock radiating heat straight back into space. A separate 2023 study of TRAPPIST-1c, published in Nature, reached an almost identical conclusion independently. Little to no thick atmosphere present, nothing thick enough to redistribute heat or shield the surface. The April 2026 measurements, led by Gillen and colleagues, extended that bare rock signature even further using updated instruments. Their team used the same thermal emission technique, timed to catch each planet at its hottest dayside point in orbit. They confirmed both B and C show the stark hemispheric split expected from an airless, tidally locked world. Neither planet showed the mid-infrared signature a thick carbon dioxide atmosphere would produce, ruling out even a Venus-like scenario for either world. 9 years separate the celebratory headlines of 2017 from the sobering confirmation of 2026. In that span, the most closely watched habitability candidates outside our solar system changed completely, planet by measured planet. From 7 Earth-sized worlds full of possibility to 2 confirmed barren rocks with the receipts to prove it, the outer planets remain under study, but no longer treated as safe bets by anyone paying attention to the data. The pattern echoes a broader lesson from exoplanet science. Initial optimism, however well-intentioned, is never a substitute for direct measurement. Somewhere in the popular imagination, though, there is already a workaround waiting, one built to feel like an escape hatch. Astronomers call it the eyeball planet. Picture a tidally locked world where the permanent dayside hosts a bullseye of open liquid water directly beneath the star, ringed outward by thickening ice as you move toward the frozen, sunless night side. This is a real, physically modeled scenario, seriously studied by climate researchers for over a decade. It genuinely represents the best-case outcome available to a tidally locked planet, not some invented loophole for comfort. Climate models built around this scenario show something sobering even in that best case. The patch of liquid water at the center of that bullseye forms a narrow ring, not a generous lake, one extremely sensitive to atmospheric pressure and composition in ways a temperature-only calculation could never capture. Push that atmosphere a little thinner, the exact direction radiation stripping tends to push it. The ring of liquid water closes up entirely, freezing solid at its former edges. Push the atmosphere a little thicker instead, and runaway greenhouse conditions can take over the entire dayside. There is no wide, forgiving margin for error built into this configuration anywhere. Researchers running these climate simulations found that surface pressure needs a fairly narrow window to hold, wide enough to keep the lake liquid, but no wider. Shift the greenhouse gas mixture even slightly, the way ongoing atmospheric stripping naturally does, and that window shrinks further, sometimes closing within a few 100 million years. Even the atmospheric composition matters here. Too much carbon dioxide relative to nitrogen tips the balance toward runaway heating, so the eyeball planet model is not evidence that tidal locking can somehow be lived with comfortably after all. It is evidence that even the single most forgiving version of this trap remains razor-thin, entirely dependent on exactly the atmospheric stability that flare-driven stripping is actively removing from the same star at the same time. Here is why none of this can be waved away as an unlucky edge case. It is not confined to a couple of unfortunate star systems. Red dwarfs make up roughly 70% of all the stars in the Milky Way. They are not the rare exception in the galaxy's stellar census. They are the overwhelming majority, outnumbering sun-like stars several times over, in nearly every direction you look. Our own solar neighborhood makes the point directly. Of the 30 or so stars within 12 light-years of the Sun, most are red dwarfs, not stars like ours. Proxima Centauri itself, the nearest star of any kind to our Sun, is one of them. Barnard's star, the second closest system to Earth, is another red dwarf entirely. Kepler and TESS survey data confirm the pattern holds well beyond our immediate neighborhood too. Every statistical claim about how many habitable zone planets exist across the galaxy follows simple arithmetic from this fact. It is mostly a claim about red dwarf planets specifically, because that is where most of that real estate physically sits. When a search for potentially habitable worlds returns a long, exciting list of candidates, something quiet happens underneath the excitement. Most of that list inherits both problems at once: flare exposure and tidal locking together, baked directly into the orbital geometry. Long before anyone even checks the atmosphere for signs of either survival or ruin. The real lie was never one single wrong planet slipping past the check. It was letting one convenient variable, distance, stand in for the majority verdict across an entire dominant category of star. None of this grim arithmetic has stopped serious researchers from asking whether the odds can still be beaten. One active line of research models whether a strong planetary magnetic field could help at all. assuming a rocky world happens to generate one on its own, the way Earth does. Such a field could deflect enough charged particles to slow the atmospheric bleed-off to survivable rates over billions of years. Earth's own magnetic field does exactly this job against the Sun's comparatively gentle solar wind, so the underlying physics here is not speculative fiction dreamed up for a documentary, but confirming whether any specific exoplanet actually has a strong magnetic field remains far beyond current instruments. A second, more exotic line of thinking proposes deliberately engineered shielding, a carefully positioned object between planet and star, or perhaps a large reflective structure, designed to blunt incoming flare intensity or redistribute heat toward the permanent night side. These proposals remain genuinely speculative for now, worth tracking rather than betting real expectations on. Nothing at this engineering scale has been tested even at the earliest concept stage yet. There is a third, quieter proposal circulating in the same research conversations, deliberately selecting older, calmer red dwarfs for future study instead of young, volatile ones. Flare activity in these stars does gradually decline with age, sometimes by orders of magnitude after several billion years. A planet orbiting an aging, settled red dwarf inherits a gentler radiation problem than one orbiting a young, turbulent star, though the tidal locking problem remains essentially unchanged either way, regardless of the star's age. None of these three approaches, magnetic shielding, engineered structures, or careful star selection, solves the problem outright yet. But together they mark where the actual frontier of this research sits now, well past the point any habitable zone diagram was ever built to describe. So follow the causal chain the whole way through now, start to finish. A dim red dwarf forces its habitable zone dangerously close in, with no alternative available. That same forced closeness delivers concentrated flare radiation, stripping atmosphere roughly 100 times faster than any solar system planet endures. That very same closeness, completely independently, locks the planet's rotation permanently, splitting one small world into a permanent furnace on one side and a permanent freezer on the other, with no atmosphere or weather left to bridge the two hemispheres. Proxima b sits inside that radiation problem today, right now, exposed to the next flare whenever it comes. TRAPPIST-1b and c sit inside both problems simultaneously. James Webb has now measured the bare rock consequence of that directly, not theoretically. Even the best theoretical outcome available, the eyeball world, survives only inside a margin too thin to call comfortable. Multiply all of this by the roughly 70% of the galaxy's stars that are red dwarfs. The supposed exception quietly becomes the overwhelming rule instead. Every one of these threads, radiation and rotation both, traces back to the identical root cause: forced physical proximity to a dim, temperamental, unpredictable star. That convergence is the real finding buried underneath everything covered so far. It is not, in the end, a reason to write off red dwarf systems entirely and stop looking. It is a reason to demand a genuinely harder question than the old diagram ever asked. A habitable zone was never meant to be a final verdict on its own. It was always just a filter with exactly one setting, checking surface temperature and ignoring everything else about the star. The actual work now underway, the work astrobiologists are doing at this very moment, looks completely different. Checking a star's specific flare history in detail, hunting for any detectable trace of a planet's own magnetic signature, carefully measuring whatever atmosphere, if any, actually survived the long bombardment. That is slower, messier work than a single green ring drawn on a diagram ever honestly promised. It is also far more scientifically interesting work, in the end, than that diagram ever suggested. It means the label habitable zone itself was never really the lie. Treating that label as the finish line, instead of the starting line, was. Picture TRAPPIST-1c one final time. Its day side baked well past the boiling point of water, its night side locked far past 200 degrees below zero. That frozen Terminator line, still running silently between the two, like an old scar across the planet's face. It sits exactly where the old diagram once said a habitable world should comfortably sit. It is dead there anyway, has been for as long as anyone can measure. That precise gap, between where the label pointed with such confidence and what the planet actually became, is the whole problem. It remains the very first thing worth checking, quietly and carefully, the next time a headline hands you another brand new Earth-like planet.